Okay, today we look at rates of reaction, and in this lesson we look at energy profile diagrams and how they can be used to understand how energy changes over the course of a chemical reaction. Some reactions are very slow. The dry corrosion of iron is an example of that. Iron reacts with oxygen. If this occurs in the absence of water, unlike here, it can take hundreds of years for it to occur. Chemical reactions can be very rapid. You drop a match into a bucket of petrol, you'll certainly find that out. Now we can best understand how the rate of reaction changes by understanding the changes in enthalpy, that is the changes in chemical energy that occur over the course of a reaction. So we've done a little bit of that before. Understand that enthalpy, otherwise known as chemical energy, is the energy stored in the compound, stored in the bonds of the compound, and that we look at delta H, the way that energy changes over the course of a reaction. So that's the enthalpy of the products minus the enthalpy of the reactants. So we looked at exothermic and endothermic reactions earlier, and combustion reactions are of course exothermic reactions. They release heat energy into the environment. So the chemicals start off with more chemical energies than they end up with, because the chemicals lose energy to get from the starting point to the ending point. That energy gets released into the environment. We experience that as heat. So an exothermic reaction you'll experience as the environment getting hotter and delta H being negative, of course, because the chemicals lose energy. Endothermic reactions, on the other hand, the chemicals absorb energy from the environment. So the chemicals start off with less energy than they end up with. Photosynthesis is the classic example of that type of reaction, when they absorb the energy from the sun and they produce glucose, which contains lots of stored energy in its bonds. So all things being equal, the environment gets colder, and because the chemicals are absorbing energy from the environment, delta H is positive. So let's look a little bit more nuts and bolts. What happens in a chemical reaction? It can be thought about as a two-step process. When we react methane with oxygen, when we burn it, the first step is the molecules collide and bonds break. So the oxygen molecules collide with the methane molecules, and we end up with those bonds being broken and atoms there ready in a high energy state, ready to combine in an alternative way. Now, in order for this to happen, the molecules have got to collide fast enough. Often orientation's important. They need to be pointing in the right direction when they collide. But if they do that successfully, the bonds will break. And then step number 2 is for the new bonds to form to create the products. So a two-step process. Bonds break, new bonds form. Why don't methane and oxygen just react? I can turn on the Bunsen burner tap over there, let the methane out, and nothing will happen. That's because the molecules aren't moving fast enough. when they bump into each other, there isn't enough energy to break the bonds in the methane molecule and the oxygen molecule. We say they lack the activation energy needed to start the reaction. So activation energy, defined as the energy required to break the bonds in the reactant molecules. So that's, in an energy profile diagram, that's the energy absorbed when the bonds are broken. Then, when new bonds form, energy is released. So, first step is for energy to be absorbed, second step is for energy to be released. That's how it looks in the energy profile diagram. So let's put it together into some energy profile diagrams. Diagrams that have a couple of features. We've got the initial level of the reactants, the final level of the products. Then in between that is the transition state. What happens when the bonds in the reactant molecules break and we get that activated state ready for the new bonds to form? So the activation energy is the rise on that graph, the height of the initial hill. How much energy you've got to put in to break those bonds. Then the energy released is the other side of the hill, how much energy gets released when the new bonds form. So here we see the overall difference between the reactants and the products. The products have got less energy, chemical energy, less enthalpy than the reactants. So the chemicals have lost energy. It's an exothermic reaction. And because the change in energy is moved in a negative direction, delta H is negative. Delta H, the overall change between reactants and products. So more energy gets released than is absorbed when the bonds break. So more energy is released when the new bonds form compared to how much was absorbed breaking the old bonds. So it's another way of looking at why its delta H is negative. Now, if we want to draw it for a particular reaction, we usually give the reactants in the energy profile diagram, we just call them 0, so the initial level is 0. Then we've got the positive direction of energy, the negative direction of energy, based on the initial level of the reactants. So that's pretty arbitrary, because really we're only interested in how the enthalpy changes. So it's always good practice to write the formulas of the reactants, write the formulas of the products. That way you can see what happens. So in this case we've got the addition reaction between ethene and hydrogen chloride. If the molecules collide in the right way, bonds will be broken, and it takes 185 kilojoules to break the bonds of 1 mole of ethene, 1 mole of hydrogen chloride. So when that happens, we've achieved the transition state, and those very reactive individual atoms can react together very readily to produce the product, chloroethane. Now when that happens, even more energy gets released. 250 kilojoules gets released for every mole of chloroethane produced. So delta H We can look at it two ways: energy absorbed minus energy released, 185 minus 250. Or we can look at it in terms of final level minus initial level. Two different ways of understanding the size of delta H. Energy absorbed minus energy released, or final enthalpy minus initial enthalpy. Endothermic reactions are the other way around. So if we know it's an endothermic reaction, we're going to draw our energy profile diagram like this, with the products being at a higher level than the reactants. So this time, a lot more energy is absorbed in breaking the bonds. We've got a very high activation energy compared to the amount of energy released when the new bonds form. So overall, the products have got more chemical energy than the reactants. We've got delta H being positive. That energy gets absorbed from the environment, so we perceive it as being colder. So an example of an endothermic reaction, the decomposition of calcium carbonate. Very high activation energy. It takes a lot of energy to break the bonds in calcium carbonate, 260 kilojoules to be precise, to break the bonds in 1 mole. So again, we put the initial level as being 0, the calcium carbonate, the reactants at being 0. So we've got an activation energy of 260, so that's the height of the initial hill. Then we know that 82 kilojoules gets released when the new bonds form. So we're going to come down 82 from 260. 260 minus 82 is 178. So that's going to be the final level of the product. In this case, energy gets absorbed, and the difference between energy absorbed minus energy released will give us delta H, so 260 minus 82 gives us positive 178. Also, final level minus initial level gives us 178 as well. Two ways of calculating delta H. Now, just a couple of things about energy profile diagrams. They are diagrams, not graphs. So we've only got one axis, which is actually a mathematical axis. That's the energy axis, the y-axis. That has a numerical scale. There is no x-axis. The x-axis does not represent time, or the horizontal direction does not represent time. It basically is the stages of the reactants. So the initial state, the transition state, and the final state. Okay, so let's draw some energy profile diagrams. So we've got a reaction up here. It's the reaction to produce ammonia, the Haber reaction. And what do we see? We see that delta H is negative 91. Straight away we see that is exothermic. Then the activation energy, the height of the initial hill, is plus 240. Well, it's always positive. It's 240 kilojoules per mole in this case. So, question A, is the reaction exactly the same as in the question? So, look at the equation, the information you're given, look at the equation for which you're being asked to draw the diagram. They're exactly the same. So we're going to use these exact numbers and the same direction. So it's exactly the same. So we know that it is an exothermic reaction. Now, we always give the initial level of the reactants 0 kilojoules. Everything is relative to that. So what is the activation energy? 240. So we'll draw an initial hill up to 240. So 0 to 240 gives us the activation energy. Next, delta H is negative 91. So we know that we're going to have to go down from 0 to negative 91 for the products. So we're going to go all the way down this side to negative 91. As soon as you know it's an exothermic reaction, you can pretty much start off by drawing that shape in which the products are way below the level of the reactants and put in the numbers from there. Okay, so how much energy is released when the new bonds form? Well, it's going to be the distance from right at the top to right at the bottom. Now I just look at the numbers. We're going all the way from 240 down to negative 91. How far is that? Well, just add them together. 331 kilojoules per mole. Now we have a look at question B, and what do we see? We see it's the same reaction, same number of moles, same coefficients, but the reaction has been reversed. Instead of ammonia being a product, ammonia is the reactant in this case. So basically all we do is we flip the energy profile diagram round left to right. So again, yeah, so flip it from left to right as I've just done there. So, whoops, I'll just go back and do that again. So that's the forward reaction. Flip it left to right, and that becomes the reverse reaction. So we've got the products way down here. Now we're going to call them 0. We know that the reverse reaction is going to be endothermic. It's going to have a delta H of plus 91. So this level here is going to be 91. And the activation energy, well, that's going to be the height of this hill. It's going to be the same as the energy released when in the previous example. So that's going to be 331. So all the way to 91 for delta H, then all the way up to 331 for the energy absorbed. How much energy was released? Well, we can pretty clearly see it's going to be that minus that, 331 minus 91, which is 240 kilojoules per mole. So that's example B. Example C is the same reaction as in B, but with the moles halved. If we halve the moles, we halve the amounts of energy in each case. So it's still endothermic, it's still going to have that basic endothermic shape, but instead of delta H being plus 91, it's going to be half that. It's going to be plus 45.5. Instead of activation energy being 331, it's going to be half that. It's going to be 165.5. And the energy released is going to be halved as well. So same shape, but just all the values have been halved. So flipping the graph from exothermic to endothermic changes the sign of delta H, and you just flip the diagram left to right. Halving the moles or changing the coefficients by a factor means that all the energy values will change by that factor as well. Okay, so let's go the other way. Let's use an energy profile diagram to calculate some values for these three reactions. So the first reaction is the reaction in the diagram as listed. B and C mean we've got to change things around a little bit. So first of all, A, the reaction as shown, and what do we see? What's delta H? Delta H is final minus initial. Now we see this is an endothermic reaction here because the products are above the level of the reactants. So delta H is going to be positive, and 128 minus 0, it's going to be 128 kilojoules per mole. Activation energy, the height of the initial hill, from 0 to 218, it's 218 kilojoules per mole. How much energy was released when the new bonds form? 218 minus 128, that's easy, 90 kilojoules per mole. So these things are really easy to get off an energy profile diagram. Okay. Second example, what we've got to do is flip the graph around. So just rotate it simply from right to left. So we rescale the axis. So the initial reactants we always give 0. That means, well, it's going to be 90 up to the top and negative 128 down to the bottom. Delta H is now negative 128 kilojoules per mole. It's gone from being endothermic to exothermic. Activation energy, the height of the initial hill, is 90 kilojoules per mole, and the amount of energy released when the new bonds form is 218. So just note that we can get those values without redrawing our whole diagram. If we go back to the initial energy profile diagram of the forward reaction, we can just work out those values simply by going backwards through the energy profile diagram. So if we go backwards for the reverse reaction, we see that the activation energy is going to be the difference between there and there, which is going to be 90. The energy released is going to be the difference between there and there, which is 218. And then delta H, if we're going backwards, is simply going to be going from here down to here, which is going to be negative 91. So you don't actually have to redraw the whole energy profile diagram. You can just go backwards through the original one to get the same result. Through that again. Now C, this time we're doing the same direction as A and we're just doubling the moles. So again, you can actually stick with the original energy profile diagram and just double all your values. Once you see there's that factor of 2 there, delta H is going to double to 256, activation energy is going to double to 436, and the energy released is going to double up to 180. Okay, pause now and have a go at the couple of questions, take a picture of them and submit them in Google Classroom, please. I'll then do the next step, multi-step reactions, on the same video. Okay, multi-step reactions, combining delta H values, where you've got two reactions that occur in a series that you can combine them in terms of an energy profile diagrams and work out what the changes in energy are going to be overall. So basically you ignore the activation energy bits and just look at the delta H bits of the energy profile diagrams. Now the key thing you have to do is make sure the mole ratios are consistent between them. So in our first reaction, first example, there are two reactions. Basically they're involving the production of sulfuric acid. First thing is that sulfur is oxidised to sulfur dioxide, strongly exothermic reaction. And then the next thing that happens is the sulfur dioxide is oxidised to sulfur trioxide, another exothermic reaction. So if we want to look at the overall change in energy, what's the enthalpy for this reaction? Well, first thing we need to do is look for the chemical which is in common between the two equations that we're combining, between the two reactions. And what do we see? The common chemical is sulfur dioxide. Now we ignore oxygen because oxygen is a reactant that occurs in most of these sorts of processes. It's the chemical that contains the sort of unique element like sulfur in this case. So, what do we need? We've got 1 mole of sulfur dioxide here, we've got 2 moles of sulfur dioxide here. That means we need to double everything in the first equation so that we've got 2 moles of sulfur dioxide in both equations. Multiply the first equation by 2. Then we're going to draw the energy profile diagram. Now, like I said before, we're going to ignore the activation energy, so it's just going to be going from initial to final. Just the delta H's are going to go in. So, what's the first one? Starting off with the reactants being 0, we've got the 2 sulphurs plus 2 oxygens gives 2 sulfur dioxides, and that's negative 594. So we're going to come down 594. So that's where we're going to end up. Second equation is 2SO2 to 2SO3, down another 197. So we're going to go from the SO2 level down to the SO3 level. That's going to take us down, as I say, another 197. So we're going to end up at 791. So what's the overall enthalpy change? Well, if we're going from 2 sulphurs right the way down to 2 sulfur dioxides, it's going to be negative 791. Okay, so let's look at another example. in which we've got carbon going to carbon monoxide. We've got carbon going to carbon dioxide. Again, in combining equations, I'm going to ignore the oxygen. It's the carbon-containing compounds that I'm going to use to combine them. And what we see, the common chemical in this case is carbon. So that's the one we need to make sure we've got the same number of carbons in each equation. We've got to get those mole ratios consistent. So the first step is to double the second equation, multiply it by 2. So we've got 2 carbons in each equation. And we can see they're both exothermic reactions. And incidentally, we see how much more energy gets released when we produce carbon dioxide. The incomplete combustion of carbon to produce carbon monoxide releases a little bit of energy, but not very much at all. The importance of having a good supply of oxygen. So, we've got our 2 delta H values to combine, and we've got carbon being the starting point for both. So they're exothermic, that means carbon is going to start off up the top and the products are going to come in down the bottom. So carbon to carbon monoxide is going to come down 221, carbon to carbon dioxide is going to come all the way down to 1574. So the reactants, the 2 moles of carbon are the same in both cases. That's 0, and then the products at the appropriate level. Don't worry too much about the oxygens. They pretty much look after themselves so long as you get the major atoms, the carbons, balanced. Now we can calculate the delta H that we're asked for, which is, what are we being asked for? 2 carbon dioxides going to 2 carbon monoxides. So this is the 2 carbon dioxide level. We're being asked to come up to the 2 carbon monoxide level. How far are we coming up? 1353 or so. And since we're going up, it's an endothermic direction. Endothermic reaction. So we can write our thermochemical equation in the appropriate form, putting in the positive, making sure we've got units, making sure we've got states, doing all the right things. Okay, now the questions. Go and do them. Again, submit them on Google Classroom. That's all for this video. When you submit your questions on Google Classroom, I'll reply with a video with the solutions.